so that I can put in YouTube. The slide is in Lentera, so you can follow the slide. I already put several slides there. You can also check. Okay. Okay, so this is what we learned last week, isn't it? Yeah. Okay. And we equilibrium, correct? And then stable and unstable equilibrium and finding the equilibrium. Right. Okay. So this is what we discussed last meeting. So today I'll continue that with some application. Okay. Oh, we also discussed about the several behavior. Right. Okay. So today we'll discuss about this demand and supply. Okay. Demand and supply model. Can you see the screen? The slide? Okay, so demand supply model of something that produce yearly or some season, based on some season. So we can try to model this. Say a farming industry. Say in the crop, a crop is produced each year. See, and then the farmer will make plan of next year crop based on the price this year. Okay, so then this is the assumption. We want to decide the price, right? So the supply of any year depend positively on the previous year price. So supply depend on the price. Okay, but the supply of this year depend on previous year price. And then demand of any year depends negatively on the present year price. Okay, so the demand depends on this year depends on the price of today, this year also. Okay, now each year price is adjusted so that the demand equal to supply. So this is the basic assumption. So now we want to know how we will model this, right? So now we say the supply of this year, okay, yeah, depends on positively. So S is positive in here, okay, and it depends on the price of last year. P is the price, K minus 1 is last year, okay, and certain parameter A. And then demand of this year depends negatively, so this one is negatively, on the price of this year, yeah, and certain parameter A and P, D and P. And then the constraint that we want is supply equal to demand, right? So this is the meaning. Yeah? So S is basically is the gradient, right? So in this case, we can say that this is the sensitivity of producer to the price, okay? And D is representing the sensitivity of the customer to the price. Okay, so then we say that S equal D. So then you can say SP K minus 1 plus A equal to minus DPK plus P, right? So, and then you can simplify, and then you will get this equation. Okay, so what is this? Can you see the equation? This equation is basically affine, right? This is the same as the one that we discussed earlier, affine difference equation. Where is the affine difference equation? Something like this, right? So yk plus 1 equal to A times yk plus B. Okay, so A and B is a constant, so the same thing here. Okay. So this is exactly the same. I will put the writing. And so yk plus 1 equal to A, or I will put it as M. Here is M. So M times yk plus intercept plus C. So this M is this minus S divided by D, and that this C is equal to this B minus A over D, right? So we know from affine difference equation the solution is stable when this value M, this minus S over D, is between -1 to +1, right? So in that case, S should be less than D. That means the customer is more sensitive to price than producer. Otherwise, the price become unstable. What is the meaning of unstable? When the price become unstable, it grow, become bigger and bigger. Okay. When stable, meaning it will narrow to a certain price. Okay, so and if the price is unstable, if S is larger than D, that means the producer is more sensitive to price than the customer. So using this simple model, we can explain, okay, for example, what happened in the oil price in 1970s. Okay, at that time there is a lack of production due to the OPEC, newly organization of the oil, and need a lot of and if they want to produce new oil, okay, they need a lot of oil exploration. So there is a delay. Because of that, the price become unstable. I think nowadays, because of the war in Ukraine and Russia, so the price is also, oil price become unstable. Okay, so what will happen when the price is unstable? Then based on this model, you can see that the government can intervene. Okay. So the government can become the big customer. Why? The purpose is to make that value of D larger. Okay, or to pay the producer not to produce, to make the D larger. So this is a few policy, okay, from this model that you can actually use. Okay, actually, if you pay the producer not to produce D larger, that means you pay the farmer so that they will not grow the crop. Sounds counterintuitive, but this is one of the policy that we can learn from this model. Any discussion you want to say? Do you understand or not? Okay, tell me what you understand about this. So, okay, this assumption, is this acceptable or not? Devi?
Yeah.
Yeah. So, and then from here, can you get this demand and supply model?
Yes.
Can you get that P here from this two? from this equation here, from these three equations here, can you get this one? Or you want to practice that? Let's do that if you want. So it's a simple algebra.
Mm-hmm.
Can you make it?
Yeah. We just like input the equation, right?
Correct. Correct. So you just put s equal,
S and
yeah, and then you just rearrange, right? So you get
yeah.
this equation, right? And you know this equation is the same as affine.
Mm,
Do you remember? We discussed last meeting about affine difference equation. Do you remember or not?
mm.
Sir, is your PPT in Lantera? Because I cannot find this one, the one you just showed.
Oh, really?
So last week is intro to discrete dynamical system.
Oh, wait. Let me open the.
Yeah, there's system dynamic, but there's no this one.
Really?
Yeah.
Let me open the lender. Ah,
Mhm.
why operation research? Yeah, okay. Is this the one? Introduction to system dynamic. Oh, okay. This was not included, so I need to update this. Okay. I need to update this information. Okay, let me delete this for a while, and then I will open again. Edit setting. I will delete for a while, and then I will update. Okay. Can you see it? Can you refresh your browser and then you can try again? Is it okay?
Yeah. I got it now, sir.
Okay, okay, good. Okay. So this is the behavior, the summary behavior of affine difference equation. Can you see that? So I just summarize it into one page so that when you have an exam or so on, you can always use this. Huh? So the difference equation is something like this, right? On the top. So yk plus 1 equal to a times yk plus b. Okay, and then if you find the solution, okay, depending on the value of a, yeah, so if a equal to 1, you get a linear model like this. Okay, otherwise it's non-linear. Okay, which part make it non-linear is the a exponent to k. This is geometric, yeah, based on the geometric series. Okay, and then the same thing with the equilibrium. Okay, that depends on the value of a. Okay, if a equal to 1, then you check the value of b. Okay, if a is not equal to 1, so the equilibrium is this value. Okay, and then stability. Okay, so this difference equation is stable if and only if, that's mean very strong, the absolute value of a is less than 1. That means between -1 and +1. Right? So this is what we used a while ago. Okay, so now if you compare this, okay, with this is called price cobweb model, right? The one that we just discussed a while ago, the demand and supply model. This one is basically a fine difference equation. Okay, so this is the parameter that determine whether it's stable or not. So we know that this is stable if minus s over t is actually between -1 and +1. Remember the absolute value of a less than 1, right? That's the same thing. Okay, and of course we can easily put it out. So that means s must be less than t. Okay, so this is to decide the stability. You see, I did not know what is the value of s. I did not know what is the value of t. I don't care. Okay, I just know the comparison of this s and t. That is the more important part there. Okay, why? Because that comparison represents the stability of this price model. So I have this is the meaning of unstable, meaning sensitive. Say the 2000 here is the stable point, right? And then unstable means you slightly deviate from the equilibrium, it will go away from the stability. Okay. So in that case, I want to ask you this behavior now, the 10 behavior that I explained last week. This one stable or not? If you look at this graph, is this stable or not? What do you think? Yeah, this is constant, so it must be stable, right? On itself. Next, how about this one? This is stable or not stable? This is linear, so unbound, so unstable. Look at the value of A. Actually, if you want to see it's stable or not, just look at the value of A, you know. So earlier, you see, this one, okay, basically this is stable, but A can be negative, yeah? But this is constant, so equilibrium, this is the equilibrium itself. Right? So this is clearly unstable. This is also unstable. How about this one? If you look at this graph, stable or unstable? Unstable. Okay. How about this one? Unstable or stable? Unstable. Okay. How about this one? Stable or unstable? K is time. So from any point, it will go to a certain equilibrium. That means stable. Is that okay? So from any point, it will go, any initial point value 0, okay, it will go to a certain value. If you look at the value of A, you see between 0 and 1. So this is stable. Okay. From the graph, you can also see. Okay. So clear, yeah? Next, how about this one? Stable or unstable?
Stable.
Stable, okay? So from any point, it will go to a certain equilibrium, right? So it's stable. And you can also check the value of A is between 0 and 1. How about this one? This is difficult to say, stable or unstable, yeah? This is actually, that's why when the value of A is equal to 1 or the value of A is equal to -1, is undecided. You see that? Yeah, stable or unstable is undecided. Yeah. So this is kind of stable because it doesn't change, right? But it's within certain value. How about this one? It's clearly, what is this? The value of A is less than -1. So unstable, right? So over time it grows, become larger and larger, unbound. How about this one? Stable or unstable? Over time, it will move towards certain value. Okay, so this is stable. Okay, and you can look, the value of A is between -1 to 0. So this is stable. Okay. Why stable and unstable is very important? Because that is how you apply. If you want to apply difference equation in real life, what you need to check is stability. Okay, not the solution. The solution is the one that we graph this, right? But the value of stability is important. Okay, so you can see if the value of A is between -1 to 1, it oscillates. Okay, it oscillates, but it will become stable. Okay, when the value of A is less than -1, okay, it oscillates and then become larger, so unstable. Okay, and exactly 1 is actually stable but oscillate with constant amplitude. Yeah? So if the value of A is between 0 and 1, okay, it doesn't oscillate. It will go to certain value. Okay, the same thing here. Okay, but if the value of A is larger than 1, you will see this is actually unstable. Okay? Unstable. So if exactly 1, we are not sure. But in this, now you check the graph, you can see that this is unbound, so unstable. Is it clear or not? So now come back to our application for price. Okay, so once you have this, then you can determine the stability based on the value of A a while ago, right? With this, in this case, become S over D. What is S? S is sensitivity of producer to the price. What is D? D is the sensitivity of customer to the price. Okay. So with this, we can start to create stability. So we know, okay, if you want to make it stable, okay, S must be less than D, right? So if the price become unstable, then you start to do something, your policy, okay, either you make it D larger or S smaller. Let's try this with a number so that you can see. Okay, I have this can you try to make it in Excel? So suppose we have this parameter here is 0.8 and then minus 1.2 and 20. Okay. And try to make this in Excel. And then check the stability. Yeah. It should be like this. The behavior should be like this. Okay, so once you make it, can you share your screen? Okay. So we'll try to write in Excel. So this is our equation. So we have Sk equal to 0.8 P K minus 1, right? And then we have D K equal to negative 1.2 P K plus 20. Okay, so then you have K here. Okay, so we have, let me put it a little bit down so that we can use it. K here, you have S, K, right? And then you have D, K, and finally you have P, K. This is the one that you plot, so we can set any value later on. Okay, we know that dk is equal to sk. Right, so in that case we just copy here. Copy this part. So we have, right, so we have dk equal to sk, so I just copy that. Right, so we have minus 1.2 pk. So let's put this all, oh sorry, yeah, it's the same. So what we have, we can put it, you want k plus 1 or k minus 1 is the same thing anyway. So now I have p k, I will put plus 1, okay, equal to 0.8. Okay, let's copy this so that you will see. This one I can put it as p plus 1. Is that okay? Plus 1, and and then this is pk. Okay, so I copy this one here, and then the minus 20 I put it on the right side. So this one become minus 20. So then this one no more, minus 20. Right? And then now everything divided by minus 1.2. Okay, let me copy. So this one divided by 1.2 minus, and then this one also divided by 1.2. So minus of minus become plus. Right. So 0.8 divided by 0.8 divided by 1.2. How much? Okay, 2/3. So minus 2/3. And then 20 divided by 1.2. 16 2/3. So this is 16.667. Right. So you can set any value here as the initial value. And then this one is just this one plus this one. So say initially P is equal to 100, right? Then what? Minus 2 divided by 3 multiplied by the previous value plus 16.66667. Okay, right. So probably you don't need S and T anymore. But if you want, you can calculate. So S is basically 0.8 multiplied by the previous pk, and then the current D is equal to negative 1.2 multiplied by the current P plus 20. And copy that. Oh, then you can plot behavior, insert. Okay, I will put it this way. Oh, you can see the price becomes stable. Is it clear or not?
Sir,
Hmm.
for the one that you write sk equal to dk,
Mhm.
that one is the constraint, or we just like make the equation between the supply equation and demand equation?
Yeah. So good question. So first time you have only these two,
Mm-hmm.
and then now you have the constraint, right? This is the constraint, right?
The constant should be sk plus 1, right? Yeah.
Same, isn't it?
Oh, it's
Okay. You want to SQ plus 1, that's fine. It's the same. Remember, this K is time, so I can put plus 1 or plus 1. As long as both sides is the same, then it's the same, right?
yeah. So it doesn't matter.
Doesn't matter. I can
Oh,
remember this is discrete, so I can add if in the left hand side I can add 1, then the right hand side also add 1. Left I add 2, then the right hand side also add 2. Okay.
Okay.
Okay. So it doesn't matter. Do you understand the meaning of this Gk equal Sk? The demand of today, K is today, equal to the supply of today. Okay. So how about this one? What is the meaning of this? Demand of tomorrow equal to supply of tomorrow. Oh, of course, right? So, but if you put like this is not the same. Demand of tomorrow equals supply of today. That is not the same.
Okay.
So if you add equal plus 1 and both sides, then it's no problem. If you want to make it parameter, so then you use this derivation 0.8 and 1.2 and so on, so that you will have actually a parameter so that you can change this value later on if you want. You can see the behavior of the price for this parameter 0.8 and what is this 1.2. Okay, this is basically minus, the value is the minus 2.3. So in that case this is the important minus 2.3, so that one less than 1. The absolute value of that is less than 1, correct? So, I mean the absolute value of minus 2 over 3 is less than 1. So it's stable. Okay. So this is the check. So initially, you can have any price. Eventually, it will stable to what price? Around 10. The value is around 10, right? 9.99 and 10, so it's very small, the difference. So, can you make it? Any question about this? Very easy. Yeah. You want to show your work?
I can share mine.
Yeah. Okay. Go.
I use Google Sheet because I don't know. I
It's the
just
same. Yeah. No problem. Wow. Okay. Become around 10, right? Yeah, 10
yes.
point something and then 9.9. Okay.
Yeah, it's here.
Correct. Right. So it's very fast to decrease. Okay. Initially, whatever value you put, it will come back to 10. You can change the 100 there to 120 or 150. Okay, 300. Again, it will come back to 10. Very fast.
Oh yeah.
Right? So regardless your initial value, so that one you can change as
Wait, so the way we interpret the price, wait, sir, how would you interpret this chart?
okay. So initial value, if the system already stable like this, okay, meaning that 0 0.8, 1.2, and 20 does not change, okay. I mean the system is already established, right? That means you don't change it. So whatever value you introduce to the market, it will come back there to 10, around 10. Over time. Okay. Initially, it can unstable, and then it will stabilize by itself. So this is what Adam Smith called as God's hand in economy. You can see that. Okay. So even if you want, even if you have a new player, say you are a new player in this farm industry. Okay, you introduce 300 initially. Okay, and then suddenly it will go down to negative. Okay, and then stabilize to eventually become meaning negative mean you get non-profit, no? Lugi. Okay. And then eventually you will stabilize to 10.
So eventually we will have to drop the price to 10 from 300.
Yes, whatever price initially you introduce in this system, okay, it will stabilize
Oh, okay,
to
okay.
that price.
So if
So
you're
this
a
is the market.
business,
Yeah, if
if
you have
you're a
business, so you
business,
know you need to create that, and then you need to check the value of that 0 0.8, 1.2. That one is the one that you uh, need to calibrate, yeah, based on the data. The model is still the same, but the value of SD, that one is the one that you need to calibrate based on the data, market data.
in real world, how do you get the value of this? By the data?
Yes, by the data, then you check. Okay. So you know if you have several price, if you have several price, say in this, say if you have several price here, you introduce new price, okay, and then you collected several prices after your introduction. Say you introduced 300, right? And you collected the price after 300, okay, in the say every week or every day, okay, then you will be able to calibrate that value, correct? You're supposed to be able to calibrate the minus 22 to over 3 and 16.67, only two values. at, at least you need at least 2 or 3 data
Okay.
to calibrate this value. Okay, so then you can this is deductive approach, yeah? Differential equation, difference equation is deductive approach. Unlike machine learning that you do inductive approach. Do you know the difference? In inductive approach, meaning you have the data and then you let the machine calculate for you and then you interpret that result, right? In deductive approach, mathematics, not statistics. Yeah? Inductive is statistics. Deductive approach is mathematics. So in that case, you create a model. You have assumption of hypothesis of the model. Okay, that model contain parameter. Then you collect the data to calibrate that model, the same like inductive approach. But because you already have very strong hypothesis, then you don't need to have a lot of data. So big data does not make it useful. I give you an example of deductive approach, okay? Exactly the same technique that the physicists are doing. For example, Newton model, okay? Isaac Newton produced gravitation model, right? Two bodies problem, which is between the moon and the sun and the earth, for example. Eh? So and then all the planetary movement is based on elliptical. Okay, that one is produced by Kepler, Johann Kepler, right? And then improved by Galileo Galilei, and then Newton creating that, based on that data, creating that model of gravitation model. You know, F equal to K times M1 times M2 divided by R squared. You remember that? In high school, you already learned that, right? So using that Newton gravitation model, okay, about 100 years later, okay, they only need 3 points of the interplanetary movement. They only need 3 points to calibrate that this planet movement is correct based on elliptical movement. Only 3 points, because for ellipse to be calibrated, you only need 3 points, right? So this is in contrast to a statistical approach that you need very big data, million of data, to create a similar model. Okay, so they both are useful. Okay, one is a deductive approach, the other one is inductive approach. So if you are dealing with only statistical approach, so machine learning, you have the data, you feed the data, and then you get the model. Okay. Yes, but in mathematics, we reverse the process. We have the model first, not you have the data and then you get the model. Okay. Here we have the model first, and then the data is just to calibrate, to fill in. That's how we use difference or differential equation. So in that case, you only need 2 or 3 points to calibrate. Yeah. Maximum 10 probably. So very fast, and now the strength of the model depends on the hypothesis that you create. Totally different approach. Can you see? Okay. Deductive approach. If you only know machine learning, you only know AI that actually based on machine learning, so data will create model. Here no, you have model first, and then you just collect data to calibrate. Can you see the difference? Okay, and both are useful, right? Because in machine learning, you don't know the model. Okay, but here you know the model. That's the difference. Okay, let's take another example. This is the arm race model of Richardson. Okay, this is very well known, and this is the lesson from history. Okay. Richardson model is called arm race model. Okay, there are 2 countries. Let's call this A and B. Okay, and AK is the country amount of budget spent for defense. Okay, and then BK again the amount of budget for defense in the year K. Okay, and these are the assumption of this model. Okay, any deductive approach should start with assumption. Okay, so this is the assumption: mutual distrust between the 2 countries. We have only 2 countries, and then almost equal economy. Okay, and then increase the expenditure of the country depends on another country, and the large expenditure of this year will be depleted, will deplete the treasury and then make smaller expenditure next year. So based on this several assumptions, Richardson proposed this model. Okay, so the difference, and you see this is actually the difference. The difference of the budget of country A depends on the value of the budget current year, and depends on the enemy's budget also. Okay, and similarly for B. Okay, and if you look at the value of R, S, T, here are the parameters. Okay, what's the meaning of parameter? Richardson say that, look, R here is actually country's A economy. Okay, the difference depends on the state. Yeah. So this is the rate of flow, and this is the state value. Okay. And S here is the distrust. Okay. Look, distrust is utility, so it's difficult to measure, but you can put any value. Okay. Now U again is economy of country B, of course must be positive. Okay. And then V in here is the distrust of B to country A. Again, utility, so you can just put any value positive. So we know that this is mutual distrust. So that is the assumption, right? So then S equal to V, and let's say almost equal economy, so we just say R equal to U. Okay, so what will happen? So once you put R equal to U, S equal to V, right? So then this is what happened. Okay, A feel in danger, right? And then country A will increase the armation, right? And then it will because country A increased the armation, country B feel in danger, right? Okay. The more country A increase the armation, country B feel in danger, and then the more country B will increase the armation. Yeah, and then the more country B increase the armation, then country A feel more in danger. Okay, and then increase again the armation. So this is a positive feedback loop. Okay, so this is called positive feedback loop. So the positive value here mean if A increase, then the armation also increase. Yeah? So if the multiplication of this sign here is positive, then this is positive feedback loop. If negative, then this is negative feedback loop. So what is the meaning of positive feedback loop? Positive feedback loop means unstable. Negative feedback loop means stable. Stable, okay? So this is unstable situation. So over time, you will see the total armation in the arm race become increase and increase. And that is actually what happened, okay? Now, in this practice, we try to simplify the Richardson model, okay, by saying only, instead of two, we simplify into one. So we just take the total, yeah? Total expenditure of A and B, so that you will get only one equation instead of two equations, okay? So again, we calculate the equilibrium, stability, and the solution, and what condition the arm race will become unstable. Unstable means what? Okay, so you add the model of these two. So remember, T equal to A plus B, right? So I just add the two of them. Okay, and we just use the algebra here. Okay, and we get the new parameter C, which is equal to W plus T. Okay, and we have A plus B equal to T, right? Because of this, we can simplify, and we have this is the new dynamical system, yeah? Difference equation. What is this? This is again affine. Can you see? Huh? This is affine difference equation, isn't it? So you know the equilibrium is this value, and this is the solution, and stability depends on this value, right? 1 minus R plus S. Okay, so it's stable if between -1 to +1. Yeah? So we can put it together. That means S minus R is between -2 to 0. Okay, what is S and R a while ago? Right, S and R is the economy and the distrust. Okay, so in that case, that depends on country restraint in this case. The restraint because of the economy is greater than the distrust. Yeah. Then if the economy is intermingled, say for example nowadays between US and China, the economy is big. Okay, even though they are mutual distrust is very big, so as long as the economy is bigger, then mutual distrust is smaller, then it will not cause war. But if the mutual distrust is actually larger, then you can see the possibility of war. Okay, and if the distrust is too great, with this S is larger than R, then the arm race will go to infinity. Okay, now depending on the initial condition, right? Then you can check in here if Tn goes to negative infinity or 0. If the initial expenditure is small enough, even if the distrust is great, the arm race will die out. But if the T0 is large, that means the economy of both sides are actually rich country. Okay, and then what happens is it will create escalating of arm race, and then there is no other way except to go to war. So this is very simple model, and this is what happened. So this is how they Richardson calibrate this model. Yeah? So before World War I, there are two alliances with is France and Russia, Germany with Austro-Hungary, okay, and then two countries, right? And then the total expenditure of the two alliances at that time using pound sterling. So, and then if you substitute this, okay, this value to the dynamical system, you can get this value, which is, you can see here, this is what? 5/3 is larger than 1, right? So in that case, when T0, in this case, the value, T0 is 199. Okay, this is the total expenditure for the alliance of defense. Is larger than 190. Here is the value. Okay, and then because of that, Tn grew exponentially, and then it will lead to World War I. Okay. And you can see actually the lesson from this mathematics. Okay, this is what happened. Currently happening, actually, right? So there is a war in Ukraine with Russia. So, and there is also alliance. Okay, so in this case NATO. Okay, and there is also possibility of alliance between China and Russia, Iran, and so on. So this become two alliance. Then if you calculate the total expenditure, which is public data, right? So you can check when, okay, based on Richardson model, when it will become actually World War III. Yeah. The mutual distrust is currently very big. Okay, so and you can see they keep adding the money for the armation. Can you see that in the news? You can check. Okay, they keep adding the money for the armation instead of negotiating for peace. They keep adding both sides. So this is a situation that is actually unstable. that can create a bigger one. This is what I mean. So you can check a very simple model of difference equation. You can predict a lot of things. And the calibration is also not so difficult. So interesting. Okay. So any comment? So using this, you can try to model anything. Okay. So okay. I will go to the next slide. This is. So I will go to the next slide. The next slide is not actually difference equation at all. This is modeling, right? But why I want to give this? If you look at the slide on system dynamic, can you open that slide? If you look at the slide in system dynamic, so okay, this is what I'll teach you. Can you open the slide?
System dynamic, right?
Correct. The modeling workshop.
Yeah.
Okay. So, why I want to give this? Okay. It seems initially I want to give this. That's why I asked your head of program, can I add this lesson, okay, in the difference equation? Because I want you to be able to actually create a model. Okay, and this is like the technique, yeah? Modeling, one of the modeling technique, yeah? So that you can understand and model anything in the world, yeah? Model anything in the world using difference or differential equation. Okay, so I will try step by step to teach you this. Okay, I hope within 1 hour we can finish. If not, we can continue next meeting. Okay. I will pass the system thinking. So basically, this is called system dynamic. I think in industrial engineering, who teach this? Did you take system dynamic class?
None that
None.
I'm
Okay.
familiar
So
of. Yeah.
okay, in industrial engineering, this is one of the main part of simulation, probably. Okay, so by my approach is different. Okay, my approach is not using software and I'm just using Excel. So you can use any software that you want, system dynamic. So in here, I just use Excel and basically just using difference equation. Okay, so should I discuss about it? Okay, anyway, so you know General Motor, the car company in the US. Okay, in 1982, they closed the plant in Fremont in California. Okay, they have the worst quality record, they have the worst labor relation, and they have the highest employee absentees and drug use. Okay, and then in 1984, Toyota, okay, bought that plant. Okay, and they hire 80% of GM workforce, and it well recorded that this is outstanding quality record. Right. The question is why? The same worker, different system. Right. So what make it different? Okay. So in GM case, the CEO get very high reward. Okay. The employee get very low reward. Okay. In Toyota system, because they use Japanese system, so it's a social system. The CEO work very hard, okay, and the salary is not that much different with the actual worker. Okay, but the discipline is very high. So, okay, so based on that, actually the actual problem is system. So what is system? System is a grouping of component and part that operate together for a common purpose. Remember, huh? Grouping of components, okay, that operate together for a common purpose. That means you need to have a purpose, a system that you want to create for your model, okay, need to have a purpose and need to have several parts, okay, and that part is some potential reality where you're concerned with space-time causal relationship. Remember, causal relationship, not correlation. It's not statistic here. Okay, it's a causal relationship. Okay, so you can think of system as a black box with input and output. Right? So example, a family is a system for, this is the purpose, living, raising the children. Example, automobile is a system consists of many parts that working together to, what is the purpose? For transportation, right? So warehouse, for example, is a system to deliver goods into trucks and so on. Management is again system, the part are the people, right? To allocate the resources to regulate their business activities. So web itself is a system, you know. Okay, so can you tell me other system? What is the component and what is the purpose? Joy, give any example and stick to that example later on.
Of a system.
Yes, a system that you are interested in. Any system.
Mm,
Devi, any system. Think about any system that you are interested in, that you want to model. And then tell me about what are the components of that system, what's the purpose of that system.
could it be an organizational system?
Yes, yes, sure.
Maybe I'll
Organization.
take that as an example.
Yeah, okay.
Yeah.
So the system of organization.
Yes. In
Yes.
Indonesia. Very.
Oh, which one? So you need to be more specific. What kind of organization?
Okay, maybe just take the one in Petra, like the student board.
Okay,
Yeah.
student organization. Okay. So the part are the people, right? Probably, or some division of them. And what's the purpose?
The purpose is the purpose of the system is basically to work efficiently to like uh, do programs that they already set in the beginning of the year
Yeah, but what's the purpose of that program?
for the students,
What, student welfare?
student welfare.
Okay, student welfare. Okay, Livy, give any example that you are interested in.
Hmm. Could it be like online class, the system of learning?
Okay, learning system. So what are components that you can think of?
Of course, the student, and then what else? The lecturer,
Okay, and
and uh, the media.
yeah, maybe the technology, right? Okay, and what's the purpose?
Uh, to find the best way of learning system.
Okay, so to educate, basically to educate,
Yeah.
right? Okay, so now next step. First is to understand what is your system. Okay, the first step, remember, huh? The second step here is to understand the structure inside your system. What does the structure mean? Okay, look, every system consists of components, right? Okay, so imagine that component represent a node. Okay, now structure is effectively interrelation, interpretation of our observation, okay, about the dynamics, okay, of this system. Okay, without an organizing structure, the knowledge, okay, mere organization, mere collection of observation, right? So basically, the structure is the one that determines the behavior of the system. Okay, so now look, any specific behavior of the system must be produced by the combination of the interaction of this component of your system. Okay, and of course that system, this component have certain boundary, right? So several things. Now you need to tell which one is internal, which one is external of your system, and then how the structure of the system that you are talking about. Okay, so this is the example. Okay, so the way to think is a causal thinking. Okay, causal thinking means that one component cause or influence or affect the other component. Can you see that? One will affect the other. Okay, so example. Okay, how do you define the causal effect? Is basically logical. Okay, so if you take more food intake, then your body weight will increase, right? Okay, if you have, say, example, if you have more money, probably increase happiness. That's okay. If there is a fire, then there is a smoke. Okay? But when we say cause and effect, is not correlation. Okay, for example, the use of seat belt will reduce the highway fatalities. In this case, it's a correlation, right? It's not really cause and effect. Okay, so many economic and sociology model is actually based on correlation, not causation. So what we want in here is causation, not correlation. Huh? Okay, this is an example. In Europe, okay, during the winter, one day is shortened by 1 hour. In that case, during that shortened daylight hour, okay, you can find the correlation of increase of suicide rate. Right? So that is again correlation, not causation. Right? So then you need to define the system boundary. Which one is included in your system and which one is excluded of yours, out of the scope of the system. So sometimes you have some difficulty to decide what level of various subsystem should be detailed enough, right? So it's sometimes difficult because the interaction between part is actually somewhat overlapping, okay? Or there is linkages with the external environment. So this is also part of difficulty in defining the boundary. Okay? But at the same time, you need to define the boundary of your system, okay, in such a way so that it will become a closed system. Okay? What is a closed system? It's a feedback system. Okay. After this, I will discuss what is closed system and open system. Yeah? So, in the concept, if you can create a closed system, then you can create a model that behavior can be determined. Okay. So, any interaction which is essential must be within that system boundary. Okay. So the building blocks of creating the system is enumerating all the parts of the system, and then you put the influence diagram. Okay, influence between one part to the other. Which part influence other part? okay, in such a way so that it will become a loop. Okay? Of course, delay can be there. Okay, now I want to discuss for the theory about what is a open and closed system. Okay, system can be classified into two. One is called open system, and the other one is called closed system or feedback system. Yeah, it's the same thing. Yeah? Feedback system or closed system is the same. So open system, okay, have characteristic that input will respond to the output will respond to the input. Okay, but uh, the output are isolated from and have no influence to the input. Can you see? Okay. There is a input to the system, and then there is an output. That is an open system. Okay. That means the system itself is not aware of its own performance. The past does not control the future. That is called open system. Okay. Give example. See, a watch on itself is an open system, right? So why? Because it doesn't adjust the, if a wrong time, okay, it will not adjust by itself. A car by itself, again, is an open system. Okay, uh, it doesn't govern by where it gone in the past or have its own goal, right? Right. So a car on itself, up to this point, still an open system. Okay. So can you find any other open system? Why this is an open system? Give example. Joy. Open system. Any system. Is your organization an open system or not?
It's a closed one, I think.
Why is it closed one and why is it there is a feedback in the organization?
Yes.
Okay. So can you find an open system without the feedback? So many, right? Actually, almost all system is a open system if you think of it.
Yeah. I think myself is an open system. I mean, I cannot evaluate like my whole bodily system.
Okay. What is your input? Your food.
Yeah.
And what is the output?
The weight.
The weight. Okay. So somehow, if you don't control, then it is an open system because you don't control it. Yeah. Okay. Right. If you don't control, meaning you don't check the weight and then you try to control your weight, then it is an open system. That's correct. Levi, give me one example of open system.
Open system.
Open system. System that only have input and output, no feedback.
How about lamp? Lamp.
A lamp.
Yeah. The input is the electricity,
Okay.
and then the output is the light itself.
The light itself. Okay. So a light bulb, right? Correct. That's an
Yeah.
open system. Correct. So now what you need to define is not an open system. What you need to define is actually a closed system. Okay. So what is a closed system? Is a feedback system. Okay. Where the result of the past action will control the future action. So probably I should share with you a whiteboard. Okay. Can you see my whiteboard? So suppose this is your system, okay, S, right? And you have an input and you have an output. So this is an open system, right? So what makes it a closed system is actually from the output, there is a feedback to the input. Okay, so the presence of feedback is the one that make it a closed system. Okay, so for example, your input is xt, your output is yt, right? So in here, the xt, say the input in here is ut. Okay, so then ut in here is equal to xt plus yt minus 1. Okay, can you see that? So there is the input depends on other input, of course, and the pass output. Is it clear or not? So that is exactly what is a feedback system. Okay, diagrammatically I show and the equation I show. Huh? So a closed system or feedback system, okay, is a closed loop structure that bring the result from the past action of the system back to control the future action. Okay, so the feedback system control action is influenced by the result of its own previous action or the past behavior. Okay, so the past will control the future or the present. Okay, that is by definition a feedback system. Okay, so of course, well-conceived system will become a feedback loop system. Yeah, so any feedback loop will involve some kind of monitoring the actual behavior of the system, and then you compare it to the behavior of standard. Okay, that's how you create a feedback loop. Okay, say in example of Joy a while ago. Okay, yes, if you put food intake and the weight by itself, okay, then it's an open system without monitoring, right? But once you start to monitor and then you compare it to a certain standard, oh, I want certain weight, right? Then you start to control the diet, for example, okay, or the amount of input and the amount of exercise that you did as an input. Then the weight as the output will be controlled as a feedback loop system, right? So the information about the deviation, okay, of that output from the standard, okay, will be inputted back to the action. Okay, so that is how you create a feedback loop. Is that okay? Okay, so remember, you have an open system or closed system. Now inside the closed system have still two categories. Okay, one is called positive feedback loop, and then the other one is called negative feedback loop. Okay, so what is positive feedback loop? It's a loop that grows. Okay, negative feedback loop is goal seeking. So if you already learned difference equation, you know this. What is this? What is this positive feedback loop? What? In difference equation jargon, this positive feedback loop means unstable. Okay? Negative feedback loop means stable. Okay. Right? Easy. So once you know the mathematics, Okay, that's the mathematics jargon, right? Now I'm talking about system dynamic jargon. Actually, the same thing, okay? But now I want to connect the two. Okay, different name of the same thing. Okay, unstable mean positive feedback loop. Okay, stable mean negative feedback loop. Okay, so positive feedback loop will generate the growth. Okay, process where the action build result that generates still greater action. Okay, it is the positive feedback form of the system structure that will find the force of growth. So you need both. In a system, you need both. The positive feedback loop is the driving force that make it grow. Okay, without positive feedback loop, your system cannot grow. For example, in a car, the gas, okay, is the positive feedback loop. The more you gas, the faster your car will move, isn't it? Right? It's a positive feedback loop. But at the same time, you need negative feedback loop, right? What? Your brake, your steering, right? That is negative feedback loop. Why? So that it will control. Okay? So you need both. Okay? If only negative feedback loop, okay, your car cannot move. Right? You only control the wheel, okay, not going to the right, left. You can control it, but at the same time, your car cannot move. Okay? You only press the brake, it will not move. Right? But you need both. Okay? If you only have the gas in the car to accelerate the car without the brake, without the steering, it will cause accident. Unstable. So you need both. Clear? In the system that you want to design, you need both. Okay? So this is an example of positive feedback loop. Okay? So bacteria, the amount of bacteria, okay, will multiply to produce more bacteria. The same thing with our cell, right? So starting from the sperm and ovum, it will grow, it doubled, become doubling, and then grow into a human being, right? So all cell growth based on this positive feedback loop initially. Yeah. Up to a certain point, then it will become the negative feedback loop will start to kick in. So what is negative feedback? Negative feedback loop will seek a goal, will stabilize, okay? Respond as the consequence of falling. If there is a deviation so much from the goal, okay, the response will become stronger. Okay? It will respond as the consequence of failing to achieve the goal. So, goal seeking, negative feedback loop is goal seeking. Okay? And, be careful, okay? The fluctuation, okay? The fluctuation is caused by this. Actually, you can check the earlier slide in the 10 behavior that I showed of affine difference equation. You can see the fluctuation happen when the value of A is between -1 to 0, right? That is a possibility of negative feedback loop. Okay, so example of negative feedback loop is air condition, right? So you can set using the thermostat. If it is too hot or it is too cool, it will, if too cool will turn off. Yeah? If it is too hot, will turn higher with the higher fan or higher machine. Okay, so the purpose is to stabilize into the proper temperature that you set, right? A watch on itself is an open system, right? But a watch with its owner now form a negative feedback loop, right? So when the watch is incorrect, the time is incorrect, then you adjust. Right? So the component is the watch itself and the owner. So two agent. Okay. Now some students, I teach this many years already. So some student will say, "Oh, I cannot find negative feedback loop." They always having difficulty finding negative feedback loop. They can only think in terms of positive, yeah, open system. Yeah, cannot make a closed system. So I said, look, that's all depends on your point of view. Okay, whether the system should be classified as an open system or a feedback system is not intrinsic to the particular assembly of part, but depends on the observer point of view, okay, in defining the purpose of the system. So you can always broaden or narrow the scope and the purpose of the system, okay, so that it will become uh, a closed system, right? Say, example a while ago, the watch itself is an open system. Okay, but when you broaden the scope, okay, now I'm not just considering the watch itself, I will consider the watch and the person that adjust the watch, then suddenly you have a closed system. Clear or not? So what to include and what to exclude in your system definition, that is the one that you can play in order to make into a feedback loop system. Okay? Remember, the one that you need to design, the system that you need to design is to create a closed system. Okay? So this is the review. Okay, there is an open system and closed system. And in the closed system, you have positive and negative feedback loop. And remember, this is depending on the observer point of view. So you can always design a feedback loop system. Up to here, is there any question first? This is just a summary. Can you create a feedback loop system? Okay. Actually, I'm supposed to give you a project so that you will pursue something, to create something. Okay. Anyway, so there is an approach, okay, in modeling to promote our understanding of event, pattern, behavior, okay, based on underlying structure. Okay, so this is called system thinking or system dynamic. Okay, so I will discuss very fast about this. Okay, three solution of system thinking is holistic, integrated solution, long-term gain, and win-win. Okay, so 1 plus 1 is not always 2. Okay, for example, two software developers work together. Usually they will produce less code than if they work separately. Right? So then the question is, why can't the whole more than the sum of its part? Right? So in fact, if in a family, okay, man and woman will produce the children. So 1 plus 1 is not necessarily 2. Okay, it becomes 3, 4, 5, and so on, right? So it's a synergy, right? So you can think of any common problem in the society, in your family, in your company or organization, and based on that common problem, now you start to create a system that you have as interest. Okay, so then you start to think why the whole is usually less than the sum of its part. Okay, that happening because each of us focus only a short-term gain and work only partial. Okay, so and then each of us probably do our best, right, to fight for the share of limited resources. So this is the problem of doing your best. Okay, so I said doing your best is not enough, right? So then how to solve that problem? You need to think in terms of holistic approach. Okay? So you pay attention of the interaction between part rather than the part itself. Okay? You're not thinking about yourself or that part that you are in, but the whole things, holistic. Okay, and then try to manage the system by managing the interaction between those components. Okay, if you want to create a system, that is the one that you need to do. Okay, uh, uh, a system may be destroyed by separately improving the performance of each part. Okay. Example here, a business traveler want to save travel department money, then they use a cheap airline connection, which costs more time and impacting his or her performance, and finally damage the purpose of the business travel, right? So they cannot sleep, okay, in the during the trips, and it will impact the business travel. So the same thing, yeah. Each department head, for example, proudly tell that their cost of saving and profit, right? So you own a company, each of your department very proud telling that what they are doing, but they forget that each cost saving is done by eliminating service from the other business unit, right? So they are not thinking holistic. They are thinking about their departmental issue. At the end, the whole company, okay, as a net decrease. Last meeting we play prisoner dilemma game, right? You remember? At that time, I said, look, the total, okay, of the system is actually reduced by competition. Okay, so in an orchestra, the players are not there to play solo or prima donna, right? But they need to support each other. The same thing with organization or family or country. Okay, we need to support each other, not just a collection of prima donnas. Now, the second system thinking solution is long-term vision. Okay, so first is integration, holistic. Second is long-term. So instead of short-term benefit, okay, you need to think in terms of long-term benefit. Okay, so I mentioned here, any person, okay, with sufficient pressure can achieve any given target number, okay, through distortion, shifting cost to others, and outright falsification. So if firefighting is rewarded, okay, as the next fire start burning. So this is a problem because now you will encourage firefighting people. Okay, if you reward the firefighter more than the long-term strategies, then people will start to behave to do firefighting. Okay, problem, just short-term problem. Okay, if you focus only the quarterly profit statement that look good today, it will have the expense for the future. Similarly, because of the fear for the appraisal, performance appraisal, right? Then they start to manage doctoring the numbers in the report, and eventually create a problem for the whole system. Okay, so long-term success and winning the environment for all come with the system thinking in practice. So this is very important. Okay, the third one is cooperation, okay, or win-win solution. So this is the one that actually create the synergy. Okay, so integrated improvement of synergy that allow individual to working within the system to achieve far more than the individual themselves. So this is the important part of this lesson. Huh? So think in terms of the group, not just individual. So we cannot separate the individual component from the performance appraisal of the whole. Okay? If you encourage individual evaluation performance, okay, then the group will be reduced. So group efforts actually should be encouraged, okay, so that people will participate in the group effort rather than the individual department or individual person. Is that clear? The way of system thinking. So I'm just laying down the foundation here so that when you want to create the system later on, okay, you know what is the goal. Okay, so the goal is to build a bigger pie rather than to fight over the pieces. Yeah? So the employees need to develop the pride and joy of their work instead of chasing the bonus. Right? So otherwise, they will start to motivate by the money, okay, not by the pride or professionality of the work. Right? So then your organization become a trouble. Okay? So now in your chosen system, how can you apply this system thinking, and in what way you think that this new approach will be beneficial? Any discussion you want to tell? Joy, Devi? A while ago you said about organization, and Devi said about learning system. So can you apply these three things: holistic, a long-term solution, and win-win solution in this system? Okay, so tell me, what is your opinion?
Yeah, I believe it can be applied to the, if an organization can perfectly apply all three, it will be very, very effective and very growing. But like in reality, most like kind, since we are like divided into like department and division,
Mm-hmm.
and we have this thing called KPI.
Mm-hmm.
Yeah, so sometimes for a department to look good, we try to bring the other down. So in
That one
comparison,
is problematic, right?
yeah,
Yes. Uh, then applying the system thinking, okay, you need to design the KPI, okay, toward a bigger goal, okay, toward the group goal rather than the individual goal. Okay, that is the connection between the bigger part of the organization with the small one. Okay. Without that connection, then it will fight for its own. And this is very dangerous because the organization will go to their own way. Right? Okay, so yeah, so just a review. Okay, so this is the three solution of system thinking: holistic, long term, and win-win. Yeah? So uh, you can read the next topic, yeah, and then I will discuss next meeting. Okay, so causal loop diagram is basically to create a very simple diagram of, say you have a component and then you draw an arrow between one component to the next. Okay, and then you put either positive or negative. Okay? Positive mean increase of one part will also increase on the other part. Decrease in one part also decrease in the other part. Okay. Negative mean the other way around. So if increase in input will decrease in output. Okay. If decrease in input will increase in output. That is the meaning of negative. Okay, and then from there you can get positive or negative feedback loop. Okay, so that is important. And then next meeting we can also practice. Okay, using that causal loop diagram we can start to practice in Excel using pulse process model. And then I will start to discuss about stock flow diagram, okay, this is the core of system dynamic. If you can actually download any software for system dynamic. Yeah? What software do you want? System dynamic software. Anyway, I usually use just Excel, but you can download Dynamo. You can download any. Check in Google system dynamic software. Power Sim probably. Okay. That you can also use. Oh, FanSim. FanSim is free. You can download FanSim if you want, so that you can drag and drop system dynamic. Oh, basically, FanSim is to draw causal loop diagram and stock flow diagram. Okay, so I will not discuss the detail of its software, of course, it's your own, but I will just discuss the theory behind, and then I will connect these two into difference equation later. Okay, so that you will know. The most important part there is actually to understand the difference between stock and flow, or maybe I should say the difference between rate and state level. Rate and level. Okay, if you can distinguish between rate and level, then you're done. Okay, and then suddenly you can start to design any system of your own. Okay, after that we come back to the difference equation again. Okay, try to read this 3 part. Okay. Okay, so no assignment for today. What else? Any question? Give me. What did you learn? Give me feedback.
We learn about feedback. No, we learn about first we learn about the supply and demand model,
Yes.
and then the war thing, the model by that guy who can predict war.
Oh,
Forgot the name.
Richardson Model. Yeah.
Yeah.
Richardson Model.
Then we learn about system
Yes.
dynamics. Yeah.
Right.
Why
System
system
dynamic.
is important and the system thinking. Yeah.
Right. Right. So yeah, I hope you can learn more. Once you pass this slide of system dynamic and the stock flow diagram, okay, suddenly you start to see, okay, oh, I know this is rate, I know this is level, right? And then after that you can say, okay, I can design anything, no, with difference equation. Okay, that is the one that I want you to do. Okay, once you know how to do that, so uh, the next step is, of course, go deeper. Yeah? So, of course, we go back to the mathematics, okay? And then we go deeper to different things. I think I put there in the uh, slide about higher order difference equation. This is exactly the same as mixing problem that you discussed earlier. Okay. So, and then I discuss in non-linear difference equation. That one I will discuss about cobweb, chaos theory, bifurcation theory, complex systems. Okay. So, if we have time, this is optional. So, if we have time, we discuss about cell automata. And if you need something else, I can look. Actually, this is very deep. We can go beyond much more beyond this. I still have one semester material actually. But anyway, so it's up to you. You can suggest what material you want me to give you. Okay, as long as within the scope of difference equation. Example, I can discuss state diagrams on state space of time series, for example. That is also within the scope of this. Yes. Anyway, I think the time is almost up. So, any question? No more? Devi? No?
Sir, maybe can I ask this like is there any system uh that cannot like the solution the one that you explain is the like the holistic long term and win-win solution. So the three of them must be applied to one system, or we
Yeah,
can
one
choose.
system. Within one system, that is the ideal.
Mhm.
Okay, the ideal is the goal should be holistic, okay, integrated, and long-term solution.
Can it just be like two?
Yeah. Again, this is an ideal, so if
Mhm.
zero is fine, right? But at the same time, of course, you want to make your system toward that goal.
Oh, okay.
Okay, so if you can have one, two, or three, that is fine.
Okay.
Is okay. Yeah? But at the same time, of course, that is not very useful system if only no long-term goal, right? No holistic. So they fight each other, so you can start to see the problem.
Okay.
Okay, good. So see you tomorrow. A different class.
Okay, thank you, sir. See you.
Okay, bye.
Sir, for the the last meeting recording, I think you can try to sign in using Zoom web.
Oh, okay. I will try.
Yeah, you can download the recording then.
Okay, I will try. Thank
Okay.
you.
Okay. Thank